Right now, as you read these words, the particles that make up your body exist in multiple states simultaneously. The electrons orbiting your atoms occupy all possible positions at once until something forces them to choose. Your hand is here and not here, solid and wave-like, determined and probabilistic. This is not philosophy or speculation. This is quantum mechanics. This is the most precisely tested theory in the history of science, and it reveals a reality so profoundly strange that even the physicists who work with it daily cannot agree on what it actually means. The hiding is not a conspiracy. The hiding happens because quantum reality resists explanation in human language. When scientists peer into the quantum realm, they find mathematics that works perfectly but describes a universe that seems impossible. The equations predict experimental results to 15 decimal places. The technology built on these equations fills your home, your computer, your phone, the LED lights illuminating your room, the medical imaging machines that save lives. All of this emerges from quantum mechanics. Yet ask a quantum physicist what an electron is doing when no one observes it, and you will receive a dozen different answers. Some will say it exists in all possible states at once. Others will claim the question itself is meaningless. A few will suggest the universe splits into parallel versions every time a measurement occurs. These are not fringe ideas debated by outsiders. These are serious interpretations defended by Nobel Prize winners, tested in laboratories, argued about in prestigious journals for nearly a century. The truth being hidden is this: reality at its most fundamental level operates according to rules that contradict everything your senses tell you about how the world works. Objects can be in two places simultaneously. Particles separated by billions of miles influence each other instantaneously. The act of observation fundamentally changes what is being observed. Empty space seethes with virtual particles that pop into and out of existence. The future can affect the past, and beneath all of it runs a mathematical structure so alien to human intuition that even understanding what the equations mean remains an open question. Here is where it begins. In the year 1900, a German physicist named Max Planck made a small mathematical adjustment to solve a problem about heat radiation. He did not intend to revolutionize physics. He was trying to match theoretical predictions to experimental data about the light emitted by hot objects. The classical physics of the time predicted that heated objects should release infinite amounts of ultraviolet radiation. This obviously did not happen. Real objects glowed red, then orange, then white as they heated. The catastrophe existed only in the equations. Planck discovered that he could fix the math by assuming energy came in discrete packets rather than continuous waves. He called these packets quanta. The word means how much in Latin. He introduced a constant, now called Planck's constant, with the value 6.626070015 times 10 to the negative 34 joule seconds. This number would become perhaps the most important constant in physics. Planck himself thought this was just a mathematical trick. He spent years trying to reconcile his quantum hypothesis with classical physics. He could not. The quantum was real. Other scientists soon discovered that light itself came in these packets, discrete bundles of energy later named photons. Albert Einstein explained the photoelectric effect in 1905 by treating light as particles that knocked electrons loose from metal surfaces. The wave theory of light, established for over a century, could not explain this phenomenon. Only particle-like photons worked. Einstein received his Nobel Prize for this discovery, not for relativity. The quantum revolution had begun, though no one yet understood how deep it would cut. Think about what this means. Light, the most familiar phenomenon in human experience, refused to fit into a single category. Sometimes it behaved like a wave, spreading out and creating interference patterns. Sometimes it behaved like a particle, delivering its energy in localized impacts. Both descriptions were correct. Both were necessary. Neither was complete. This was not a limitation of measurement or a gap in knowledge waiting to be filled. This was nature itself speaking in paradoxes. The strangeness multiplied through the 1920s. In 1923, Louis de Broglie proposed that if waves could behave like particles, perhaps particles could behave like waves. He calculated that every object with momentum should have an associated wavelength. For everyday objects like baseballs or cars, this wavelength was absurdly tiny, far too small to detect. But for electrons and other subatomic particles, the wavelength was significant. His doctoral thesis committee nearly rejected his work as too speculative. They consulted Einstein, who endorsed the idea. De Broglie received his PhD. 4 years later, experiments confirmed that electrons indeed created wave-like interference patterns. Particles of matter behaved like ripples spreading through space. The double-slit experiment demonstrates this impossibility with elegant simplicity. Take a barrier with 2 narrow slits cut into it. Fire electrons one at a time toward the barrier. Place a detector screen behind it to record where each electron lands. If electrons are particles, you expect 2 bright bands on the detector screen, one behind each slit. Run the experiment. Instead, you see an interference pattern, alternating bands of many electrons and few electrons. This is the signature of waves. Waves passing through both slits spread out and overlap. Where the peaks of one wave meet the peaks of another, they reinforce and create brightness. Where peaks meet troughs, they cancel and create darkness. Electrons somehow pass through both slits simultaneously and interfere with themselves. Here is where it gets uncomfortable. Modify the experiment to determine which slit each electron actually passes through. Add detectors at the slits themselves. Run the experiment again. The interference pattern vanishes. The electrons now create 2 simple bands, acting like classical particles. The act of observation changes the outcome. Not because the measurement apparatus disturbs the electrons with clumsy interactions. The effect persists even with the most gentle, indirect measurements physicists can devise. The electron seems to know it is being watched and alters its behavior accordingly. This is not metaphor. This is not interpretation layered onto data. This is what happens in laboratories worldwide, replicated thousands of times, confirmed beyond any doubt. Send one electron through the apparatus. It passes through both slits as a wave, interferes with itself, and lands at a position determined by the wave interference. But the moment it hits the detector screen, it arrives as a single point, a localized particle. The wave function collapses. All the spread-out probability condenses into one definite outcome. Before measurement, the electron existed in superposition, simultaneously taking all possible paths. After measurement, it exists in one specific state. The measurement itself forces reality to choose. What is the electron doing between emission and detection? Standard quantum mechanics offers a straightforward but unsatisfying answer. It exists in a superposition of all possible states. Its position is not merely unknown, it is genuinely undefined. The electron is not hiding somewhere along a definite path that we simply have not measured. It occupies all paths at once with different probability amplitudes. The mathematics describes this using wave functions, complex valued functions that encode the probability of finding the particle in different states. The wave function evolves smoothly and deterministically according to the Schrödinger equation, named for Erwin Schrödinger, who formulated it in 1926. Then measurement happens, and the wave function collapses instantly and randomly into one outcome. The equations describe this process perfectly. They cannot explain why it happens. Calculate what happens next. In 1927, physicists gathered in Brussels for the 5th Solvay Conference. The greatest minds in physics debated the meaning of quantum mechanics. Niels Bohr championed what became known as the Copenhagen interpretation. It held that quantum mechanics provides a complete description of reality, but reality itself is fundamentally probabilistic. Before measurement, particles do not possess definite properties. They exist in superposition. Measurement creates definite values. This is not ignorance. This is ontology. Reality at the quantum level is indeterminate. Albert Einstein objected strenuously. He argued that quantum mechanics must be incomplete, that some deeper theory with hidden variables would restore determinism and objectivity. God does not play dice with the universe, he famously insisted. Bohr replied that Einstein should stop telling God what to do. The debate became philosophical because the experimental predictions of quantum mechanics worked flawlessly. Regardless of interpretation, physicists could calculate the probability of any measurement outcome and match observations to arbitrary precision. The theory succeeded as an algorithm for predictions. What it described about the nature of reality remained disputed. This tension persists today. Quantum mechanics is simultaneously the most empirically successful theory ever devised and the least understood at a fundamental conceptual level. The math works. The meaning remains hidden behind a veil of mathematical formalism and competing philosophical frameworks. Something else was happening, discovered through careful analysis of quantum systems. In 1935, Einstein collaborated with Boris Podolsky and Nathan Rosen to publish a paper arguing that quantum mechanics could not be a complete description of reality. They presented a thought experiment now known as the EPR paradox. Create two particles that interact and then separate, moving apart to vast distances. Quantum mechanics predicts that measuring a property of one particle instantaneously determines the corresponding property of the other particle, regardless of the distance between them. The particles exist in an entangled state, a single quantum system split across space. Measure the spin of one electron as up. The other electron must have spin down. This correlation appears instantaneously. Einstein found this result absurd. He called it spooky action at a distance. Special relativity prohibits any influence from traveling faster than light. Yet quantum entanglement seemed to require instantaneous correlations across arbitrary distances. Einstein argued this proved quantum mechanics was incomplete. The particles must carry hidden information determining their properties all along. They do not suddenly acquire definite spins when measured. They already possess those spins, predetermined when they separated. The apparent quantum randomness simply reflects our ignorance of these hidden variables. The argument was compelling. It was also wrong. In 1964, physicist John Stuart Bell derived an inequality that any theory of local hidden variables must satisfy. Local means influences propagate at or below the speed of light. Hidden variables means properties exist independently of measurement. Bell showed that quantum mechanics violates this inequality for certain experiments. The predictions of quantum mechanics and local hidden variable theories diverge in measurable ways. This elevated a philosophical debate into an experimental question. Test whether nature obeys Bell's inequality or violates it as quantum mechanics predicts. The first experiments came in the 1970s and 1980s, performed by physicists like John Clauser, Alain Aspect, and Anton Zeilinger. They created entangled photons, separated them, measured their polarizations, and compared the correlations. Nature violated Bell's inequality. Quantum mechanics was correct. Local hidden variable theories failed. The experimental evidence has only strengthened over decades. In 2022, Clauser, Aspect, and Zeilinger received the Nobel Prize in Physics for these experiments. Their work confirmed something profoundly strange. Entangled particles behave as a single system regardless of the distance separating them. Measure one, and you instantly gain information about the other. The correlation is not predetermined. The particles genuinely lack definite properties until measurement, and yet the correlations appear instantaneously across space. This does not enable faster-than-light communication. You cannot control what result you get when measuring an entangled particle. The outcome is random. Only when comparing measurements of both particles do the correlations become apparent. No information travels between the particles in any conventional sense. Nevertheless, entanglement reveals that quantum systems cannot be understood as collections of independent particles with local properties. The universe exhibits a kind of holism at the quantum level. Parts of a system remain connected in ways that defy spatial separation. Pay attention to this detail. The experiments ruling out local hidden variables came decades after the theory predicted them. For over 30 years, physicists worked with quantum mechanics, built technologies with it, taught it to students, all while a fundamental question about its interpretation remained unsettled. This pattern repeats throughout quantum physics. The math races ahead of understanding. Predictions are made and confirmed while debates about what those predictions mean continue unresolved. The quantum realm reveals its secrets through equations that we can manipulate but cannot fully comprehend. The measurement problem stands at the heart of quantum confusion. Before measurement, a quantum system exists in superposition, described by a wave function that evolves deterministically. During measurement, the wave function collapses, and the system randomly selects one outcome from the superposition. This collapse happens instantly and irreversibly. The Schrödinger equation describes the smooth evolution of superposition. It does not describe collapse. Collapse must be added as a separate postulate, an additional rule grafted onto the theory. Why does collapse happen? When does it happen? What counts as a measurement? Standard quantum mechanics provides no answers. Schrödinger himself highlighted the problem with his famous cat thought experiment, published in 1935. Place a cat in a sealed box with a quantum device. A single radioactive atom has a 50% chance of decaying within 1 hour. If it decays, a detector triggers a mechanism that kills the cat. If it does not decay, the cat lives. According to quantum mechanics, before you open the box, the atom exists in superposition of decayed and not decayed states. The cat, entangled with this atom through the detection apparatus, must also exist in superposition. The cat is simultaneously alive and dead. Only when you open the box and observe does the wave function collapse and the cat become definitely alive or definitely dead. Schrödinger intended this as a reductio ad absurdum, demonstrating that something was wrong with applying quantum superposition to macroscopic objects. Cats are not simultaneously alive and dead in any meaningful sense, yet the quantum formalism seemed to require this conclusion. Where does superposition end and definite classical reality begin? Does collapse happen when a conscious observer looks? When a detector clicks? When the radioactive atom interacts with the detector? When the poison is released? The theory does not say. It cannot say while remaining internally consistent. The Copenhagen interpretation sidesteps the problem by asserting a fundamental division between the quantum system and the classical measuring apparatus. Quantum objects exist in superposition. Classical devices yield definite outcomes. Measurement is the boundary crossing between quantum and classical realms. This works for practical calculations but leaves the boundary vague and arbitrary. All measuring devices are ultimately made of atoms that obey quantum mechanics. How does classical definiteness emerge from quantum superposition? Here is where competing interpretations diverge most sharply. The many worlds interpretation, formulated by Hugh Everett in 1957, eliminates wave function collapse entirely. Superposition never ends. When a measurement occurs, the universe splits into multiple branches. In one branch, the cat is alive. In another branch, the cat is dead. Both branches are equally real. You only perceive one branch because your consciousness becomes entangled with that outcome. The other version of you in the other branch perceives the other outcome. Every quantum measurement spawns countless new branches, a ceaselessly proliferating multiverse containing all possible outcomes. This interpretation preserves determinism. The universal wave function evolves smoothly according to the Schrödinger equation at all times. There is no random collapse, no special role for measurement. Everything that can happen does happen in some branch of the multiverse. The apparent randomness of quantum outcomes reflects your ignorance of which branch you inhabit. Before measurement, copies of you exist in superposition across many branches. After measurement, each copy observes a definite outcome, and the branches decohere, effectively splitting into separate realities that can no longer interact. Many physicists find this interpretation extravagant. It postulates an uncountable infinity of unobservable parallel universes to avoid wave function collapse. Occam's razor suggests preferring explanations that do not multiply entities beyond necessity. Creating an entire universe every time an electron's spin is measured seems excessive. Yet the mathematics of many worlds is arguably simpler than Copenhagen. It requires no additional collapse postulate. The Schrödinger equation suffices. The multiplication of worlds is a consequence of taking the equation seriously at all scales, not an ad hoc addition. Other interpretations offer different resolutions. De Broglie-Bohm pilot wave theory, developed in the 1920s and 50s, adds hidden variables back into quantum mechanics in a non-local way. Particles always have definite positions, guided by a quantum wave that evolves according to the Schrödinger equation. The wave is real but distinct from the particle. It encodes information about the entire experimental setup and guides the particle's motion. This restores determinism and definiteness to quantum mechanics at the cost of introducing action at a distance. The pilot wave responds instantaneously to changes throughout space, violating locality but preserving the statistical predictions of standard quantum mechanics. Objective collapse theories modify the Schrödinger equation itself, adding terms that cause wave functions to spontaneously collapse when systems reach a certain size or complexity. Superposition works fine for single particles. As systems grow larger and more entangled with their environment, collapse becomes increasingly likely until macroscopic objects exist in definite states at all times. This approach treats collapse as a real physical process, not a mysterious boundary between quantum and classical. The cost is introducing new physics beyond standard quantum mechanics. Experiments have begun testing these theories by searching for deviations from standard quantum predictions for increasingly large superpositions. So far, standard quantum mechanics holds. Watch what happens when we zoom into the details of how superposition actually ends. This is where quantum decoherence enters the story, developed primarily in the 1980s and 90s by physicists including Wojciech Zurek, Erich Hughes, and Juan Pablo Paz. Decoherence does not solve the measurement problem completely, but it explains much of why we never observe quantum superposition in everyday life. The key insight is that no system is truly isolated. Even the most carefully controlled laboratory experiment cannot perfectly shield a quantum system from its environment. Photons bounce off the system. Air molecules collide with it. Thermal radiation interacts with it. Each environmental interaction entangles the system with the environment. Consider an electron in superposition of two positions. The electron is here and there simultaneously. Photons from the surrounding environment scatter off the electron. A photon that bounces off the electron at position here carries different information than a photon that bounces off the electron at position there. These photons fly off into the environment, becoming entangled with countless other particles. The information about the electron's position spreads through the environment at the speed of light, becoming rapidly inaccessible. The electron remains in superposition in a technical sense, but the interference between the two positions becomes unobservably small. The system behaves as if it has collapsed into one position or the other. This is decoherence. The mathematical structure of decoherence is elegant. The density matrix describing the quantum system develops off-diagonal terms representing quantum coherence, the interference effects that signal superposition. Environmental interactions suppress these off-diagonal terms exponentially fast. For macroscopic objects in ordinary environments, decoherence happens absurdly quickly. A dust particle in air loses quantum coherence in about 10 to the negative 31 seconds. A 1 kilogram object decoheres in 10 to the negative 40 seconds. This is why we never see tables or chairs in superposition. Environmental interactions destroy superposition faster than it can manifest at observable scales. But decoherence does not truly solve the measurement problem. It explains why superposition becomes unobservable. It does not explain which outcome gets selected when measurement occurs. In the many worlds interpretation, decoherence explains the branching of worlds. Environmental entanglement splits the universal wave function into effectively separate branches. In Copenhagen, decoherence explains why we observe classical definiteness, but still requires collapse to select one outcome. The question of what happens during measurement remains partially hidden behind the math of decoherence. Something remarkable emerges when we examine how physicists test quantum mechanics with ever more sophisticated experiments. In 1978, Wheeler proposed the delayed choice experiment, a modification of the double-slit experiment that pushes the paradox further. Set up the apparatus so you can choose whether to measure which slit information after the photon has already passed through the slits, but before it reaches the final detector. If you choose to measure which slit, the photon should behave like a particle, passing through one slit or the other. If you choose not to measure, it should behave like a wave, passing through both slits and creating interference. But you make this choice after the photon is already on its way. Does it pass through one slit or both? Experiments performed in the 1980s and later confirmed Wheeler's prediction. The photon's behavior depends on your future choice. If you will measure which slit, it passes through one slit as a particle, even though that measurement has not happened yet. If you will not measure, it passes through both slits as a wave. This is not the future changing the past in a time travel sense. The photon never had a definite path until measurement forced it to choose. The apparent retrocausality emerges from insisting that particles must have been doing something definite before measurement. they were not. They existed in superposition of all possibilities. Your delayed choice simply determines which observable you measure, which question you ask reality to answer. The answer was never determined until you asked. Researchers have pushed this effect to cosmic scales. In 2015, experiments achieved delayed choice quantum erasure using entangled photons across kilometers. More ambitiously, astronomers have proposed delayed choice experiments using photons from quasars billions of light years away. The photon has been traveling for billions of years. Its path curves around a massive galaxy, acting as a gravitational lens, potentially taking two different routes around opposite sides of the galaxy. Set up detectors on Earth to either measure which path the photon took or measure the interference between both paths. Your choice determines the photon's history billions of years ago. This has not yet been performed with true cosmic photons, but nothing in quantum mechanics forbids it. The implications are staggering. Another quantum phenomenon challenges intuition in different ways. Quantum tunneling allows particles to pass through energy barriers that classical physics forbids. Imagine rolling a ball toward a hill. If the ball lacks sufficient energy to reach the top, it rolls back down. It cannot possibly end up on the other side of the hill. Quantum particles disobey this limitation. An electron encountering a barrier has some probability of appearing on the other side, even if it lacks the energy to classically overcome the barrier. The particle's wave function extends through the barrier. On the other side, the amplitude is reduced, but non-zero. Measure the particle, and it might be there. Tunneling is not a metaphor or approximation. It is essential to nuclear fusion in stars. The protons in the sun's core move too slowly to overcome their electromagnetic repulsion and fuse together. Classical physics predicts the sun should be dark and cold. Quantum tunneling allows a small fraction of protons to penetrate the energy barrier and fuse, releasing the energy that powers the sun and makes life on Earth possible. Every photon warming your skin traverses billions of quantum tunneling events in the sun's core. Alpha decay in radioactive atoms occurs through tunneling. The nucleus traps alpha particles in a quantum potential well. They lack sufficient energy to escape. Yet occasionally, an alpha particle tunnels through the barrier and flies free. This process has been understood since the 1920s, verified in countless experiments, and incorporated into every model of nuclear physics. Reality permits quantum particles to exist temporarily in forbidden regions. Tunneling highlights another quantum strangeness. The time it takes for a particle to tunnel through a barrier appears to be nearly instantaneous, potentially even zero, regardless of barrier width. This is the Hartmann effect, observed in experiments but not fully understood. Photons tunneling through barriers seem to cross them faster than light would travel the same distance in vacuum. This does not violate relativity because no information can be transmitted this way. The effect depends on quantum properties established before tunneling, not on superluminal communication. Nevertheless, the phenomenon suggests time itself behaves strangely at quantum scales. The implications ripple outward into technology. Modern electronics depend fundamentally on quantum mechanics. Transistors in computer chips work through quantum effects in semiconductors. Electrons tunnel through insulating barriers in flash memory. Scanning tunneling microscopes image individual atoms by measuring the tunneling current between a sharp tip and a surface. Quantum mechanics is not abstract theory. It is the foundation of the digital age. This creates a paradox in itself. We build technologies with quantum mechanics without agreeing what quantum mechanics means. Engineers design quantum devices using the equations as a cookbook. Calculate the wave function. Apply the Schrödinger equation. Compute measurement probabilities. Build the device. It works. The physical reality described by those equations remains disputed. The disconnect between practical success and conceptual confusion is unlike anything else in science. Consider the quantum vacuum, the state of lowest energy where no particles exist. Classical physics treats vacuum as empty space, devoid of content or activity. Quantum field theory reveals that vacuum seethes with virtual particles, fleeting fluctuations allowed by the uncertainty principle. Heisenberg's uncertainty principle, formulated in 1927, states that certain pairs of properties cannot simultaneously have definite values. The most famous version involves position and momentum. Measure a particle's position precisely and its momentum becomes highly uncertain. Measure momentum precisely and position becomes uncertain. The uncertainty is not a limitation of measurement technology. It is a fundamental property of nature. Position and momentum do not simultaneously exist as definite values. Energy and time form another uncertain pair. At sufficiently short timescales, energy becomes uncertain. This allows virtual particles to briefly violate energy conservation. An electron can spontaneously emit and reabsorb a photon, existing temporarily with more energy than it should possess. The photon exists for a time inversely proportional to its energy, then vanishes. These virtual particles cannot be observed directly because observing them would require sufficient energy to make them real. Nevertheless, their effects are measurable. The Casimir effect demonstrates this directly. Place two uncharged metal plates very close together in vacuum. Virtual photons of all wavelengths constantly fluctuate in and out of existence in the space between the plates and outside them. Inside the gap, only virtual photons with wavelengths shorter than the gap width can exist. Longer wavelengths are excluded. Outside the plates, all wavelengths contribute. This creates an imbalance in radiation pressure. More virtual photons push on the outside of the plates than push from inside. The plates are forced together by vacuum fluctuations. This effect was predicted in 1948 by Hendrik Casimir and measured in the 1998 with precision by Steve Lamoureux. The force is tiny, about 1 atmosphere of pressure for plates separated by 10 nanometers. But it is real and measurable. The vacuum is not empty. It is a churning sea of quantum fluctuations. Virtual particles also affect the properties of real particles. An electron in empty space constantly emits and reabsorbs virtual photons. These interactions subtly change the electron's measured mass and charge. Quantum electrodynamics, the quantum theory of electromagnetism developed in the 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, accounts for these effects through a process called renormalization. Calculations in QED predict the electron's magnetic moment to 11 significant figures, matching experiments to the same precision. This is the most accurate prediction in the history of physics. It depends entirely on treating virtual particles and vacuum fluctuations as real physical phenomena. Here is the troubling part. Calculating the energy density of quantum vacuum fluctuations produces an answer that is catastrophically wrong. Sum the energy contributions from all possible virtual particle fluctuations up to the Planck scale, the shortest distance where quantum mechanics and gravity both matter. The result is approximately 10 to the 94th grams per cubic centimeter. This number is so enormous that a teaspoon of vacuum would contain more energy than all the visible stars in the universe. Observe the actual energy density of the vacuum, measured through cosmological observations of the universe's expansion rate. The value is about 10 to the negative 29 grams per cubic centimeter. The theoretical prediction exceeds observation by 123 orders of magnitude. This is called the cosmological constant problem. It is perhaps the worst prediction in physics. Something does not add up. Quantum mechanics requires vacuum fluctuations. These fluctuations have measurable effects like the Casimir force. Yet the total energy they contribute to space-time curvature is somehow nearly zero, vastly smaller than calculation predicts. Physicists have no widely accepted explanation. Proposals range from unknown symmetries that cancel positive and negative contributions to anthropic arguments involving the multiverse. The quantum vacuum simultaneously explains some of the most precisely verified predictions in physics and generates one of the most profound mysteries. The truth about the vacuum's energy remains hidden behind this colossal discrepancy. Nobody expected what came next in quantum mechanics. In the 1980s and 90s, physicists and computer scientists realized that quantum superposition could be harnessed for computation. A classical computer stores information in bits, each either 0 or 1. A quantum computer uses quantum bits, or qubits, that exist in superposition of 0 and 1 simultaneously. A single qubit can be 0, 1, or any quantum superposition of both. 2 qubits can exist in superposition of 4 states simultaneously. 3 qubits encode 8 states. N qubits represent 2 to the power of n states at once. A quantum computer with just 300 qubits could represent more states simultaneously than there are atoms in the observable universe. This does not mean a quantum computer can try all possibilities simultaneously and instantly find the answer. Measurement collapses the superposition, yielding only one outcome. The power of quantum computing comes from clever algorithms that choreograph quantum interference. The superposition evolves according to the Schrödinger equation, allowing different computational paths to interfere constructively and destructively. Correct answers interfere constructively and become more probable. Wrong answers interfere destructively and become less probable. Measure the final state, and you are likely to get the right answer. Quantum algorithms can solve certain problems exponentially faster than any known classical algorithm. Shor's algorithm, developed by Peter Shor in 1994, can factor large numbers efficiently using a quantum computer. Factoring is the mathematical problem underlying most modern cryptography. Current encryption relies on the practical impossibility of factoring numbers with hundreds of digits. Classical computers would require longer than the age of the universe to factor such numbers. A sufficiently large quantum computer could factor them in hours. This threatens to break much of internet security. Researchers race to develop quantum-resistant cryptography before large-scale quantum computers become practical. Grover's algorithm, published in 1996 by Love Grover, searches unsorted databases quadratically faster than classical algorithms. If a classical algorithm requires n steps to search n items, Grover's algorithm requires only the square root of n steps. This is not exponential speedup, but it applies to a broader class of problems. Quantum simulation algorithms allow quantum computers to efficiently simulate other quantum systems, a task exponentially difficult for classical computers. This could revolutionize materials science, drug discovery, and fundamental physics research. Building practical quantum computers faces enormous challenges. Qubits must maintain superposition long enough to perform calculations. Decoherence from environmental interactions destroys superposition rapidly. Modern quantum computers operate at temperatures near absolute zero to minimize thermal fluctuations. They use elaborate error correction schemes, encoding logical qubits in multiple physical qubits, so errors can be detected and corrected before destroying the calculation. The overhead is immense. thousands of physical qubits might encode just one error-corrected logical qubit. Nevertheless, progress accelerates. In 2019, Google announced quantum supremacy, demonstrating a quantum computer performing a calculation impractical for classical computers. IBM, Microsoft, Amazon, and numerous startups invest billions in quantum computing research. The first practical quantum computers may arrive within the next decade. The technology rests entirely on phenomena that seem impossible. Quantum computers work by placing particles in superposition, entangling them across the processor, and exploiting interference between different computational paths. Every calculation confirms the reality of superposition and entanglement. Every successful quantum algorithm validates quantum mechanics at a technological scale. We are building machines powered by the strangeness at the heart of reality. Machines that function precisely because particles can be in multiple states simultaneously and influence each other instantaneously across space. Quantum cryptography offers another application, one already commercially available. Traditional cryptography relies on the computational difficulty of certain mathematical problems. Quantum cryptography exploits the laws of quantum mechanics themselves to guarantee security. The most developed form is quantum key distribution. Alice wants to send Bob a secret message. First, they need a shared encryption key unknown to any eavesdropper. Alice sends Bob qubits encoded in photon polarizations. Eve tries to intercept and measure these photons, but quantum mechanics forbids Eve from measuring the qubits without disturbing them. The no-cloning theorem, proved in 1982 by Wouters and Zurek, states that arbitrary unknown quantum states cannot be copied. Eve cannot measure the qubits and send perfect copies to Bob. Her measurement collapses the superposition, introducing errors that Alice and Bob can detect. If they observe too many errors, they know someone is eavesdropping and discard the key. If errors remain low, they use the key to encrypt messages with provable security guaranteed by the laws of physics. Several companies already sell quantum key distribution systems. Fiber optic links in Europe and China distribute quantum encrypted communications. China launched a satellite called Michius in 2016, specifically for quantum key distribution, achieving quantum encrypted communication between ground stations separated by thousands of kilometers. The technology transitions from laboratory curiosity to practical infrastructure. Your future communications may be secured not by clever mathematics, but by the fundamental impossibility of observing quantum systems without disturbing them. Each quantum technology validates the theory by functioning exactly as equations predict. The predictions emerge from mathematics that we still cannot fully interpret. We fly quantum airplanes without agreeing whether the wings truly exist before we look at them. This strange separation between operational success and interpretational confusion continues to characterize quantum mechanics a century after its discovery. Return to the measurement problem with fresh perspective. Recent experiments probe the quantum classical boundary with unprecedented precision. Physicists have demonstrated quantum superposition in increasingly large objects. In 2011, researchers achieved superposition of mechanical resonators visible to the naked eye. In 2010, experiments created superposition states of molecules containing hundreds of atoms. In 2019, the Virgo and LIGO gravitational wave detectors began accounting for quantum uncertainty in the motion of their 40-kilogram mirrors. These mirrors reflect laser light to measure distortions in space-time from colliding black holes billions of light years away. Quantum mechanics predicts a fundamental noise in their position, uncertainty about where they are at any moment. This quantum noise became measurable in the detectors, requiring correction in the data analysis. 40-kilogram mirrors exist in a haze of quantum uncertainty. How far does superposition extend? Can arbitrarily large objects exist in superposition, or does some new physics enforce collapse at a certain scale? Experiments inch toward answering this question. The current record involves molecules with over 2,000 atoms in superposition. Plans exist for demonstrations with viruses, bacteria, perhaps eventually microscopic crystals. Each step requires more sophisticated isolation from decoherence. The expected outcome, based on standard quantum mechanics, is that superposition continues indefinitely. No fundamental size limit restricts quantum behavior. Only practical decoherence from environmental interactions creates the appearance of classical definiteness. But the experiments must be done. Nature may surprise us. The quantum Zeno effect demonstrates another counterintuitive phenomenon. Zeno of Elea, an ancient Greek philosopher, proposed paradoxes about motion. One paradox suggests that an arrow in flight is at rest at every instant, so motion is impossible. The quantum Zeno effect inverts this. Continuously measuring a quantum system can freeze its evolution. A radioactive atom in superposition of decayed and undecayed states will eventually collapse to the decayed state. But if you measure whether it has decayed at very short intervals, the repeated measurements keep resetting the superposition, preventing decay. The atom becomes frozen in its initial undecayed state by constant observation. This has been confirmed experimentally. The act of measurement not only collapses superposition, but can prevent quantum evolution entirely. The inverse quantum Zeno effect also exists. Under certain conditions, frequent measurements can accelerate rather than inhibit quantum transitions. Both effects demonstrate that measurement is not passive observation, but active interaction that fundamentally alters quantum systems. The notion that we simply learn pre-existing values when we measure becomes untenable in light of such phenomena. Measurement creates the values it reveals. These experimental advances occur alongside continued debates about interpretation. Polls of quantum physicists at conferences reveal no consensus. The Copenhagen interpretation remains most common, but far from universal. Many worlds has gained adherents, particularly among quantum computing researchers who work daily with superposition and entanglement. Some physicists refuse to endorse any interpretation, treating quantum mechanics as a calculational tool without ontological import. Others develop new interpretations. Quantum Bayesianism, or cubism, treats quantum states as expressions of personal belief rather than objective reality. Relational quantum mechanics argues that quantum states are relational, defined only relative to particular observers, with no observer-independent quantum state existing. The proliferation of interpretations shows no sign of resolution. This interpretational landscape reveals something profound about quantum mechanics. The theory may be instrumentally complete while remaining conceptually open. We can predict every measurement outcome with arbitrary precision. We cannot say what exists between measurements in a way that all physicists accept. The mathematics constrains predictions tightly, but leaves ontology underdetermined. Multiple, incompatible descriptions of reality yield identical experimental predictions. Nature hides the truth not by concealing facts, but by revealing mathematics that supports multiple, equally valid interpretations. Scientists have discovered additional quantum phenomena that deepen rather than resolve the mysteries. Weak measurement, developed in the 1980s and 90s, allows extracting limited information from quantum systems without fully collapsing their wave functions. By weakly entangling a measuring device with the quantum system, then measuring the device, you gain partial information while leaving the system mostly undisturbed. Repeating this process on many identically prepared systems allows reconstructing the quantum state. More strangely, weak measurement can yield values outside the allowed range for standard measurements. A spin that should measure either up or down might yield a weak measurement value of 100 times spin up. These weak values, though named values, do not represent pre-existing properties. They are artifacts of the quantum measurement process itself, yet they are measurable and reproducible. Contextuality represents another quantum feature without classical analog. The outcome of measuring a quantum observable depends on what other observables you measure simultaneously or sequentially. Measuring the spin of an electron along the x-axis gives one set of probabilities. Measuring along the z-axis gives different probabilities. But the result of measuring along x depends on whether you measured z first, and in what basis. The electron does not simply possess definite spin components along all axes simultaneously. The measured value depends on the context of measurement. This has been proven mathematically and confirmed experimentally, eliminating the possibility that particles carry hidden instruction sets specifying outcomes for all possible measurements. The quantum world is irreducibly contextual. None of this is mysticism or interpretational overlay. These are mathematical theorems and experimental facts. Bell's theorem proves that local realism is incompatible with quantum mechanics. The Kochen-Specker theorem proves that quantum observables cannot consistently be assigned predetermined values independent of measurement context. Leggett's inequality extends Bell's work to rule out certain non-local hidden variable theories. Experiment after experiment confirms quantum predictions and rules out classical explanations. The strange features of quantum mechanics are not artifacts of limited knowledge or measurement imprecision. They are properties of nature itself, as firmly established as any facts in science. The universe operates on principles that contradict everyday experience. Objects exist in superposition until measured. Particles instantaneously correlate across cosmic distances. Measurement outcomes depend on context. The vacuum seethes with fluctuations. Time behaves strangely near barriers. Observation can prevent change. These are not philosophical speculations or mathematical curiosities. They are the verified structure of physical reality. The hiding occurs because this structure resists translation into human language and classical concepts. Zoom outward to see how quantum mechanics connects to the largest scales. Cosmology and quantum mechanics intersect at the universe's beginning. The Big Bang theory describes the universe expanding from an extremely hot, dense state approximately 13.8 billion years ago. Running the expansion backward leads to a singularity, a point of infinite density and temperature where general relativity breaks down. Quantum mechanics must become important at these extreme conditions. Yet we lack a complete theory of quantum gravity that consistently combines quantum mechanics with Einstein's general relativity. The best current framework is quantum field theory in curved spacetime, treating quantum fields on a background of curved spacetime specified by general relativity. This hybrid approach works reasonably well until distances shrink to the Planck length, approximately 10 to the negative 35 meters, and energies reach the Planck energy, around 10 to the 19 billion electron volts. At these scales, quantum fluctuations of spacetime itself become significant. The smooth spacetime continuum assumed by general relativity dissolves into quantum foam, a seething uncertainty in the geometry of space and time. We have no confirmed theory describing physics at the Planck scale. String theory, loop quantum gravity, and other approaches attempt to quantize gravity, but none has achieved experimental confirmation or widespread acceptance. Despite this limitation, quantum mechanics plays a crucial role in early universe cosmology. The cosmic microwave background radiation, discovered in 1965 by Penzias and Wilson, carries information about the universe when it was 380,000 years old. Tiny temperature fluctuations in this radiation, measured to 1 part in 100,000 by satellites like COBE, WMAP, and Planck, represent the seeds from which galaxies and large-scale structure grew. These fluctuations originated as quantum fluctuations in the inflaton field during cosmic inflation, a hypothesized period of exponential expansion in the first fraction of a second after the Big Bang. Inflation theory, proposed by Alan Guth in 1980 and refined by many others, suggests that the universe underwent a brief period of extraordinarily rapid expansion, driven by a scalar field in a false vacuum state. Quantum fluctuations in this field were microscopic, but inflation stretched them to cosmic scales. When inflation ended, these quantum fluctuations became density variations in ordinary matter and radiation. Gravity amplified the denser regions over billions of years, forming galaxies and clusters. Every star, every planet, every structure in the universe traces back to quantum fluctuations expanded to cosmic size. You exist because of quantum uncertainty in the first instance after the Big Bang. This is testable. Inflation makes specific predictions about the statistical properties of the cosmic microwave background fluctuations. The angular power spectrum, describing how temperature varies on different angular scales across the sky, matches inflationary predictions remarkably well. The fluctuations are nearly scale invariant, meaning they have similar amplitude at all scales, as inflation predicts. They are Gaussian, matching the expected distribution from quantum fluctuations. They are adiabatic, meaning the density fluctuations affect all components of the universe equally, consistent with a single quantum field driving inflation. Alternative theories without inflation struggle to explain this combination of properties. Inflation also predicts the existence of primordial gravitational waves, ripples in space-time produced by quantum fluctuations of gravity itself during inflation. These would leave a distinctive signature in the polarization of the cosmic microwave background, called B-mode polarization. Several experiments search for this signal. In 2014, the BICEP-2 experiment announced a detection of B-modes that could be from inflation, generating enormous excitement. Subsequent analysis showed the signal was mostly from dust in our galaxy. The search continues with increasingly sensitive instruments. Detection would provide direct evidence that quantum fluctuations can affect space-time itself, a quantum gravity effect observable across the cosmos. Quantum mechanics also governs the ultimate fate of black holes. Stephen Hawking predicted in 1974 that black holes emit thermal radiation due to quantum effects near the event horizon. Virtual particle pairs constantly form from vacuum fluctuations. Near a black hole's event horizon, one particle can fall into the black hole, while the other escapes. To an outside observer, this appears as thermal radiation emitted by the black hole. The black hole loses mass and energy through this Hawking radiation, eventually evaporating completely. For stellar mass black holes, this process takes vastly longer than the current age of the universe, but it demonstrates that black holes are not truly black. They glow with quantum radiation. Hawking radiation creates the black hole information paradox. When a black hole forms from collapsing matter and then evaporates via Hawking radiation, what happens to the information encoded in the matter that formed it? Hawking radiation is thermal, random, carrying no information about what fell into the black hole. This seems to violate quantum mechanics, which requires information to be conserved. Pure quantum states must evolve into pure states, never into mixed thermal states that have lost information. Either quantum mechanics fails, general relativity fails, or something more subtle occurs that allows information to escape the black hole in ways we do not yet understand. Physicists have grappled with this paradox for decades. Recent work using holographic principles from string theory suggests that information is encoded on the black hole's event horizon and gradually released in subtle correlations in the Hawking radiation. The information is not lost, but scrambled in the most complex way possible. Recovering it would require capturing all the Hawking radiation and performing impossibly sophisticated quantum computations. But in principle, the information survives. This resolution remains debated and not fully proven, but it points toward a deeper connection between quantum mechanics, gravity, and information theory. The holographic principle itself represents a profound quantum insight. It suggests that all the information contained in a volume of space can be represented by a theory on the boundary of that space. The three-dimensional universe might be a hologram, a projection from information encoded on a two-dimensional surface. This idea emerged from studying black hole entropy. Jacob Bekenstein and Stephen Hawking showed that black hole entropy is proportional to the area of the event horizon, not the volume. This suggests that the maximum information in a region is proportional to its surface area. The ADS-CFT correspondence, discovered by Juan Maldacena in 1997, provides a concrete mathematical realization of holography in certain spacetimes. A quantum gravity theory in a space with negative curvature is exactly equivalent to a quantum field theory without gravity on the boundary of that space. This duality suggests that space-time itself might be an emergent phenomenon, arising from more fundamental quantum information. These developments push quantum mechanics into realms where space and time themselves become quantum and perhaps emergent. The strangeness compounds. Not only do particles exist in superposition and entangle across space, but space itself may be a macroscopic approximation of an underlying quantum structure. The true degrees of freedom may not be particles in space, but quantum information from which space emerges. This is highly speculative, but it is pursued seriously by theoretical physicists seeking to understand quantum gravity. Return to Earth and consider the role of quantum mechanics in biology. For decades, biologists assumed quantum effects were irrelevant to life. Cells are warm, wet, messy environments where decoherence should destroy quantum coherence almost instantly. Classical physics seemed sufficient to explain biological processes. This assumption is now questioned. Quantum effects appear to play functional roles in several biological systems. Photosynthesis converts sunlight into chemical energy with nearly 100% efficiency. Light harvesting complexes in plants and bacteria capture photons and transfer the energy to reaction centers. Classical models predicted significant energy loss during transfer. Experiments in 2007 by Graham Fleming and colleagues revealed quantum coherence in light harvesting complexes at room temperature. The excitation energy exists in superposition across multiple pathways simultaneously, allowing the system to efficiently explore all routes and funnel energy along the optimal path. Quantum coherence persists for hundreds of femtoseconds, far longer than decoherence times predicted for such warm, disordered environments. The protein structure may protect quantum coherence through noise-assisted transport, where environmental fluctuations actually enhance rather than destroy quantum efficiency. Avian navigation may use quantum entanglement. Many bird species navigate using Earth's magnetic field during migration. The mechanism remained mysterious until cryptochrome proteins in bird eyes were proposed as quantum magnetoreceptors. Cryptochrome contains pairs of electrons that become entangled when the molecule absorbs blue light. Earth's weak magnetic field influences the quantum spin state of this entangled pair. Different orientations relative to the field produce different chemical reaction rates, which the bird detects as a visual signal. This has been demonstrated in isolated cryptochrome molecules and is consistent with behavioral studies. Birds may literally see the magnetic field through quantum entanglement. Enzymes catalyze chemical reactions essential for life. Many enzymes work through quantum tunneling. Protons and electrons tunnel through energy barriers, enabling reactions that would be impossibly slow classically. Hydrogen bonding in DNA relies partly on quantum tunneling of protons between bases. Mutations may occur when protons tunnel to incorrect positions. Quantum effects in enzyme active sites allow reactions to proceed at biological temperatures and speeds. Life exploits quantum mechanics not despite decoherence, but through evolved mechanisms that channel quantum effects toward functional outcomes. These findings remain debated and require further confirmation. If validated, they suggest that biology is not purely classical, but harnesses quantum phenomena in warm, complex environments. Evolution discovered quantum advantages long before human physicists. The boundary between quantum and classical is not a hard threshold, but a complex landscape where organisms may exploit quantum resources under certain conditions. Life itself may be a quantum phenomenon. Consider where this leaves us. Quantum mechanics is the most successful theory in physics, tested and confirmed to extraordinary precision over a century. It underlies the technology of the modern world. It describes phenomena from subatomic particles to cosmic scales, from the first instance after the Big Bang to the distant future of black holes. It may even play functional roles in living organisms. And yet, we cannot agree on what it means. The mathematics is clear and unambiguous. The Schrödinger equation, the uncertainty principle, the Born rule for calculating probabilities, the tensor product structure of composite systems. These mathematical structures are among the most precisely specified in all of science. Apply them correctly, and you can predict experimental outcomes with arbitrary precision. The empirical adequacy of quantum mechanics is unmatched. The ontology remains opaque. What exists between measurements? Is the wave function physically real or merely a calculational tool? Does collapse actually happen? If so, when and why? If not, what explains the appearance of definite outcomes? Do particles have properties before measurement? Does consciousness play a role? Is reality deterministic or fundamentally random? Does the universe split into branches? These questions have multiple incompatible answers, all consistent with experimental evidence. This situation is unique in modern physics. Classical mechanics, thermodynamics, electromagnetism, general relativity all come with broadly accepted ontologies. We may argue about details, but we agree on the basic picture. Classical particles follow definite trajectories. Heat is molecular motion. Electromagnetic fields carry energy and momentum through space. Space-time curves under the influence of mass energy. Quantum mechanics offers no such consensus. The map is astonishingly accurate. The territory remains disputed. Some physicists embrace this situation. Shut up and calculate, the saying goes. The theory works, predictions agree with experiments, that suffices. Ontological questions are meaningless or unanswerable. Physics describes phenomena and their relationships, not the nature of reality. This instrumentalist view has pragmatic appeal. It allows physicists to work productively without resolving interpretational debates. Other physicists find instrumentalism unsatisfying. Science aims to understand reality, not merely predict observations. A theory that works while remaining fundamentally incomprehensible is incomplete, regardless of its predictive success. The measurement problem is not a philosophical diversion, but a genuine gap in the theory. Quantum mechanics tells us how to calculate what happens when we measure, but does not explain what measurement is or why it has special status. This seems like a hole at the theory's center. The debate is not idle philosophy. Different interpretations suggest different research directions. If many worlds is correct, the universal wave function contains all of physics. Understanding its structure and evolution becomes paramount. If collapse theories are correct, finding the mechanism and threshold for collapse opens new physics beyond standard quantum mechanics. If hidden variables exist, searching for experimental signatures that distinguish them from standard quantum mechanics could revolutionize physics. If consciousness matters, understanding the mind-matter interface becomes a physics problem. The interpretation you adopt shapes what questions seem important and what experiments seem worth doing. Recent decades have seen this philosophical debate become increasingly experimental. Tests of Bell's inequality rule out local hidden variables. Tests of contextuality confirm quantum predictions. Searches for spontaneous collapse have begun. Quantum computing explores superposition at engineered scales. These experiments do not yet decisively favor one interpretation over others, but they transform metaphysical speculation into empirical investigation. The nature of quantum reality may eventually be resolved not by philosophical argument, but by experimental test. Until then, the truth about quantum reality remains partially hidden, not by scientific secrecy, but by the structure of quantum mechanics itself. The theory presents us with a map of exquisite detail and accuracy, but drawn in a language we have not fully learned to read. The symbols are precise, the predictions infallible, but the meaning unsettled. Reality at the quantum level operates according to rules we can write down, manipulate, and exploit while being unable to say definitively what those rules describe. This is the secret scientists are hiding, though hiding is the wrong word. They have discovered a description of reality so successful in practice, yet so resistant to interpretation that a century of effort has not resolved fundamental questions about what it means. Particles exist in superposition. Entanglement connects distant objects. Measurement collapses wave functions. Vacuum fluctuates with virtual particles. Quantum effects underlie technology, structure the universe, perhaps support life. All of this is confirmed beyond any reasonable doubt. What it implies about the nature of existence remains open. As you lie here considering quantum reality, remember that the particles constituting your body are quantum objects. The electrons in your neurons exist in superposition until their wave functions decohere through interaction with the environment. The chemical processes sustaining your life involve quantum tunneling. The photons entering your eyes have traveled in superposition from their sources. You are made of quantum phenomena, not classical substances. The strangeness of quantum mechanics is not remote abstraction, it is the foundation of your physical existence. The search for understanding continues. New experiments probe larger superpositions, test longer coherence times, search for quantum effects in unexpected domains. Theoretical physicists develop new interpretations, refine existing ones, seek experimental signatures that distinguish them. Quantum technologies advance from laboratory demonstrations to commercial products, making quantum mechanics ever more tangible. String theorists and quantum gravity researchers try to extend quantum mechanics to space-time itself. The next century of quantum physics may finally resolve the interpretational questions that have haunted the theory since its inception. Or it may reveal deeper mysteries, stranger phenomena, more profound questions about the nature of reality. For now, quantum mechanics stands as humanity's most successful, yet least understood theory. The equations work, the technology functions, the predictions match observations to 15 decimal places. And the ontology, the description of what actually exists and how, remains contested by brilliant physicists with access to identical data. This is not failure, this is the frontier of knowledge, the edge where human understanding meets reality's deepest structure. The truth is not hidden by conspiracy or secrecy. It is hidden by being so strange that our classical intuitions and language fail to capture it, even as our mathematics describes it perfectly. The quantum world follows rules we can write but not fully comprehend, rules that govern everything from the smallest particles to the largest structures, from the beginning of time to its end, rules that perhaps permit multiple equally valid descriptions of reality, or reveal that reality itself is more subtle than any description can capture. This is where physics stands today. This is what quantum mechanics has taught us. And this is why, a century after its discovery, physicists still argue about what it means while agreeing completely on what it predicts. If this journey through quantum reality has resonated with you, if these strange truths about the universe have sparked wonder or curiosity, there are deeper mysteries waiting to be explored. The quantum realm is not the only place where reality defies intuition. Space-time bends, time dilates, horizons trap light, and existence unfolds in ways that challenge every assumption we bring from everyday experience. Leave your thoughts in the comments. Tell me which quantum phenomenon surprised you most. Ask questions that trouble you. And until next time, remember that you are not merely in the universe observing it. You are made of quantum particles in superposition, entangled with everything around you, participating in the strange dance of reality at its most fundamental level. Sleep well, fellow traveler through the quantum cosmos. The wave function collapses around you, but perhaps, somewhere in some branch of the universal superposition, all the other versions of you are collapsing in different ways, and all of it is real.